transformers, basic operation, assumption for an ideal transformer, impedance ratio or reflected impedance, and solving transformer problems using that method. So that is essentially what the first transformer session is about, and it's around using the concept of an ideal transformer to then be able to develop a model for a real one that's got, so you can analyze the losses and find out why you actually don't quite get out what you think you're going to get out of a transformer. Okay, so that's the idea anyway. So on the second slide, I did a little bit about transformers and why, really. I mean, the main use of them is on the national grid, you know, in terms of power circuits, step up, step down. So we generate at about 25 kilovolts, step up to as much as 400 on a supergrid, and then back down again in various different stages depending on who's taking electricity. Some are 33 kV, 11 kV, and eventually down to the 400 stroke 230 that we've been looking at in our star delta systems. Yeah, so very, very widely used power system, as well as the tiny little things you see in power supplies and what have you around the place. Okay, I don't want to dwell on that too much. The basis around transformers is that if you start with an AC coil and you pass an AC voltage through it, you'll have a magnetic field build up as the voltage builds up, falls away as the voltage drops back to zero, build up in the opposite direction, and then collapse again. So you've got this constantly expanding and collapsing magnetic field that's also changing direction. Yeah, so if you looked at that, this north and south pole would constantly be switching over as you went through the AC waveform, but very quickly. Okay. If we then place another secondary coil in close proximity to the first one, no electrical contact in terms of conduction of electricity, but what we've got then is we've got an expanding and collapsing magnetic field in the first coil that's actually cutting across the conductors in the second coil, and that induces a voltage in that second coil. So what we end up with, by passing an AC voltage into that coil, we actually get an AC induced voltage in this coil, and there's no electrical connection between the two, just a magnetic coupling. Okay, so the term for that is mutual inductance. You're mutually inducing this voltage into this coil by the proximity of that one. Yeah. Changing the magnetic field in the primary coil induce a voltage in the secondary coil. Simple method like that of just pulling two coils close to each other would be very inefficient, because you're losing a lot of the field, a lot of it's stray, and that's not coupled. Okay, so what we need to do is come up with a way of improving the linking of the flux. So what they tend to do is put the coils onto an iron core that is in this most basic form, circular, primary wound round one side, secondary wound round the other. That tends to concentrate the magnetic field, because it would rather exist inside that iron core than it would in air, and so we get a much better linkage and a much more efficient transformer. And in actual fact, what they would do is have this kind of shape in the most basic transformer, iron core, laminated together. The laminations prevent losses, because they prevent current setting up around in the core. They're insulated from each other, but they put both the windings around there, primary and secondary, over top of each other, again getting those two magnetic fields as close as possible together. Right? So again, we've got this primary voltage, magnetic field building up and dropping away, cuts across the conductors in the secondary core and induces a voltage at the terminals. So if we connected a load to this end, like so, you get a current flow. Okay? And then cores, ferromagnetic, very low resistance to flow and flux compared with the surrounding air. So most, I didn't ought to put all there really, most of the flux flows through the iron core. Now you're always going to get a little bit of leakage, as we're going to talk about as we go on. Okay? So we'd have primary voltage, primary current, the number of turns on the primary coil, number of turns on the secondary, current in the secondary, voltage at the terminal of the secondary coil. Yeah. So that terms we're generally going to be dealing with as we go through our work with transformers. The ideal transformer. From Faraday's law of electromagnetic induction, the voltage in the primary coil is equal to the number of turns on that coil multiplied by the rate of change of flux with time. Because it's like there's self-induction in that primary core by Faraday's law. Okay? And the voltage at the secondary terminals is equal to the number of turns on the secondary coil times the rate of change of flux. Now, because the magnetic flux is common to both sides, the rate of change of flux is the same on both sides. So that term is equal. So what that means is we can write that V1 over N1 is equal to V2 over N2, or we can write V1 over V2 is equal to N1 over N2. Now, the ratio of the primary and secondary voltages is equal to the ratio of the primary and secondary turns. That's what we're interested in here, is this part. The ratio of primary to secondary is equal to the ratio of the turns on the primary to the turns on the secondary. None of those quantities have got any units. They're ratios. How much bigger is the primary voltage than the secondary? How many more turns is there on the primary than there is on the secondary? Okay. If a transformer is 100% efficient, so apparent power is also preserved, that means the apparent power S on the primary side in VA, we're going back a little bit now to what we did earlier, apparent power as your volt amps, is equal to the apparent power in a secondary. That all must be the case for 100% efficiency. If that's the case, then I1 times V1 must equal I2 times V2. If we then rearrange that, we find that the ratio of primary to secondary is equal to the ratio of a secondary to primary. And if you remember, of those three, voltage, number of turns, current, the current one is always the other way up. The reason for that is, you're all reasonably aware, I would hope, that transformers can step voltage up or step it down, but you can't step them both up. If voltage is going to go up, the current's going to go down. Voltage goes down, the current will go up. To be able to preserve that truth of S1 equal and S2. Yeah? If those two weren't equal, we'd have a problem, because we'd be either be creating or getting rid of energy, and we can't do that. All right? So the full ideal transformer equation is there. N1 over N2, V1 over V2, I2 over I1. And we could equally, if that's convenient to us, turn all of them up the other way and use them the other way round. All right? Everybody happy with that? And I'm sure Steve went through that before anyway. Yeah, and if you've done any kind of basic electrics with transformers, you'll have done ideal transformer. So, what are the assumptions made for an ideal transformer? Before we undertake looking and analysing a real transformer, we need to first examine what the properties of so-called ideal transformer. By definition, they have the following properties. No losses due to core heating, eddy currents, or the resistance of the windings. You're making the assumption that the windings ain't got no resistance. There's no eddy currents flowing in the iron core, and it doesn't heat up. Yep. Its core is infinitely permeable, i.e., what that means is it will, while you keep adding flux, it will take it, and you can't. There's no limit to the amount of flux you could apply to that iron core. Again, in reality, that isn't true. And the coupling between the primary and secondary, the magnetic coupling I mean there, is perfect. So that all the flux produced by the primary is completely linked by the secondary, and the flux to the secondary is completely linked with the primary coil. No leakage at all. And that in real terms, that's not possible either. Okay, so if you make all those three key assumptions, then that transformer model of V1 over V2, N1 over N2, I2 over I1 is true. Yep. With these assumptions in place, the apparent power supplied to the primary will be equal to the apparent power delivered to the secondary, i.e. it will be 100% efficient. Wouldn't that be lovely? Yep. And this one, infinitely permeable, what we have is, if we look at flux build up as we add current or add amp turns, there's a limit to how much flux B we can get into that core, and then as we come back down again, that goes like that, and you end up with what's called a hysteresis diagram for that core. And the wider that is, the less efficient it is, really. Yeah, because it doesn't return back to where it started and all sorts of things. So you've got losses involved in there. To get that perfect thing, you'd need a hysteresis curve like that, where it could carry on adding flux forever, go perfectly back to nothing when you turned it off, and all the way into negative flux down that way. I don't know of any ferrous or other magnetic core that will do that. Alright? So all still okay. Alright, Richard? Yeah. So, by way of example, and I believe these are in the notes, electrical system, 124 volt AC, input to the site is 14.4 kV AC. What's the required turns ratio of the transformer to achieve this voltage step down? So, what we're interested in is that the turns ratio is N1 over N2, and we know that from the transformer equation is equal to V1 over V2. So it's like kind of anything that over that, 14,400 over 120 is 120 to 1. Yeah. So we'd have, for every 120 turns on the primary coil, we'd have 1 turn on the secondary coil, if it was 100% efficient. The secondary current is 500 amps. What's the primary current? So again, we apply the formula N1 over N2 over N1 times I2 is equal to I1. We get a primary current of 417 amps. So that kind of shows you where the voltage is high, the current's low, and vice versa. So if we step voltage down, current goes up in the secondary, and vice versa. Okay. Assuming an ideal transformer, confirm the conservation of power. So P1 is equal to P2, V1 times I1, 14,500 times 4.16, 120 times 60,000. Yep. So the idea of doing that is to show that both sides are conserving the power. Yep. All fairly simple stuff, and you're probably well aware you ain't going to get that question in the exam. All right. So, did you go through this question? Ideal transformer, 1200 turns. Let's just see, I've probably got a worked answer in here. Yeah. 100 volts, yeah. 8 and a third, yeah. 2.08. 3 VA. So are you all happy with that? Yeah. Yeah. The worked answers. I've got a set of worked answers here, and they were the results. So Steve will have gone through those. I'm trying to get to the bit where we didn't do anything more. Okay. Also, what I've got is, for the tutorial questions, I'll stick your set of worked answers to them up as well, so you can have a look through there. There'll be something like that on there anyway. Right, turns ratio, the ideal transformer. Defining the turns ratio as the letter A simplifies some of the calculations that we're going to be doing around transformers. So rather than keep writing N1 over N2 down, I'm going to use the term A to be the transformer ratio, and it is always N1 over N2. Therefore, if I step down, that's going to be a number bigger than 1, and if I step up, that's going to be a fraction, a number smaller than 1. Yep. But the turns ratio A is always N1 over N2. Yeah. If we do that, because I is N1 over N2, all right, and E1 over E2 is equal to N1 over N2. Yeah. E1 over E2 is equal to A. Yeah. Therefore, E1 is equal to A times E2. Yeah. All happy with that? Also, we've got I as N1 over 2. N1 over N2 is equal to I2 over I1. Again, remember, it's the other way up. Yep. Therefore, I is equal to I2 over I1, and therefore I1 is equal to I2 divided by I. We're going to be using those a lot, right? Because this transfer and impedance method of analysing transformers involves us using those formulae there to transfer a voltage from the primary to the secondary side and then back again to do the analysis. Alright, more about that later. So that's where that comes from, and that's why it's far easier to write A and use A there as the ratio, N1 over N2, always remember it, okay, than it is to keep writing N1 over N2. So in summary so far, we've got that the voltage on the primary is equal to the turns ratio times E2, and the primary current is the secondary current divided by the turns ratio. Notice that they are opposites of each other, so as you change something, one goes up and the other one goes down. Yeah? The turns ratio for a transformer is a constant. Okay? Yeah. Now, impedance ratio. Did Steve do this bit? Yeah? Did you get it? Yeah? Because it's about, we've got a generator on this side with an ideal transformer of turns ratio A there, feeding a secondary that's supplying an impedance Z. This is around what impedance does that generator see? Yeah? Because it doesn't see, if Z is 10 ohms, the generator doesn't see 10 ohms unless the transformer ratio is 1. Yeah? So that's what this is around. So what's the reflected impedance? What does the generator see? Yeah? And what I tend to call that is Z dash. Yeah? He done it like that, did he? Yeah, good. So we got this reflected impedance on the right hand side. Yeah, when we move, or this is what the generator sees. So it's like saying, what would I do to connect to that generator so that I've only got that and all the transformer and everything else disappears? It's what the generator sees. And we think what you should have somewhere is that the reflected impedance Z dash, yeah, is equal to A squared Z. Yeah. So when you transfer an impedance, the generator sees, or what the impedance that the generator sees is the turns ratio squared times the actual impedance. Yeah. Okay. You're happy for me to move on? Yeah. So then there's an example, 50 ohm resistor connected to the secondary of a transformer with the turns ratio of 1 to 25. Calculate the impedance seen by the source connected to the primary. Yep. Did you do that one? Yeah, because here we got, so I is 1 over 25, which is 0.04. Yeah. What we're looking at here is a circuit where a generator is connected through a transformer I equals 1 over 25 to a secondary that's got a 50 ohm resistor in it. Yeah, that's the circuit we're looking at. So Zg is equal to Z dash, which is A squared times 50. That's 0.04 squared times 50. I think that come out at 0.08 ohms. Does that ring true for a transformer that's got a turns ratio 1 over 25? Does that step up or step down? Step up, yeah. Yeah. So you're going to get more or less current in the secondary. You ain't got no voltages, so you don't really know, but you'd expect that impedance to be lower, wouldn't you? Yeah. Alright? Happy? Happy? Yeah? Sorry, that's the impedance of generator C, so that side's going to have more current. Yeah? That low impedance there is going to cause more current to flow in this side than it is in the actual secondary. Yeah? Which is right for a step up, because voltage goes up, current goes down. Yeah? Okay? Just trying to show you how you can notice whether you're gone slightly wrong by the fact that you know whether that transformer step up or step down. Yeah. Next one, following example illustrates how effective value of a capacitor can be changed using a transformer. 10 microfarad capacitor connected to a transformer with a ratio of 1 to 5. The frequency of the supply is 50 Hertz. Calculate the impedance seen by the generator and the value of the capacitance seen by the generator. Did you do that problem? Yeah? And you should have had, for A, 318 ohms. Yeah? Sorry, ZC is 318 ohms, so that the impedance, this is the circuit, so there's the generator. There's our ideal transformer, and I is a fifth, yeah. And then we've got this capacitor here, alright, that's 10 microfarads. That works out to, at that frequency, 318 ohms. Yep. Transferring that to the other side, so that's like having over here, ZC dash comes out to 12.7 ohms. Yep, so that's part A, final answer. And then part B, you use the 1 over 2 pi FC formula to calculate, and you get 250 microfarads. So using the step-down transformer, you turn a 10 microfarad capacitor into a 250 microfarad capacitor. Anyone think what the disadvantage there of that is? Yes, you've made the capacitance bigger, but what's the disadvantage there? Think about the turns ratio and whether I step up or step down. Step up. So you've got to have a capacitor, that 10 microfarad capacitor has got to have 5 times the working voltage it would than if you got a 250 microfarad capacitor to directly connect to the generator. So there's always a trade-off. It will help you if you ain't got a 250 microfarad and you're desperate for one. Right? The only reason I can think of going the other way, i.e. making a capacitor smaller, is that you haven't got the one you need. So really, I'm not sure whether this is a technique that might normally be used. I've never heard of it being used, but it shows you that you can vary the values of components by putting the transformer in between them. All right. So you're all happy with that one? Steve done that one quite ably. Looks like it. Yeah. Right. Then what we move on to is solving transformer problems by shifting impedances. Yeah. So there's a method. What we've got here is transformers, and this is kind of the real transformer model, but we haven't talked about what these components are yet and what they represent. Okay, so there is a prelude to what we're doing, what we're going to do next week, or maybe start a bit later today, is look at the real transformer and how we represent the losses in a transformer model. So it's kind of preempting that. So we're going to look at the calculation method first. Did he cover this? No. He might have done one with some values because he found having values easier. Maybe. I don't know.
Yeah, he said one of your questions he'd answer and he could find the correct answer, he can find it correct, so he done his own.
Okay. Well, what we'll do is we'll go through these, I think, and then we'll know where we are, and that's a way to ease back into it. All right? So, method. One. Shift Z2 to primary. What that means is Z2 dash, Z2 transferred the primary side is equal to A squared times Z2. So that's using that stuff we done on the previous page. Yeah. Oh, Matt. Like I said, the first thing is, and what we're effectively going to do here, is take this impedance, Z2, and shift it so that's on the primary side. And that means it's got a different value, Z2 dash, and we'd calculate that by multiplying Z2 by transformer ratio squared. Yep. Second thing we do is shift to the secondary voltage, E2, this one, to the primary side. So we'll put that over there. So that's part 2. Shift E2 to primary. And from what we talked about earlier, that would become E2 with a dash, and that would be equal to I times E2. Hang on, this is bloody... Hold on. Shift E2 to primary. Essentially, E2 dash is equal to I times Z2. And then again on our circuit, what we really need to do is, say we've got a secondary current there, 3 transfer I2 primary, i.e. I2 dash is equal to I2 over A. That one's the other way up. When we've done that, this is the circuit we've now got that we can analyse. So there's our generator. I1. There's their Z1 resistor. Okay. Z2 dash, we've shifted. E2 dash, that is, sorry. Z2 dash there. And here's our transformer, which we really can leave off, but that's where it is. That's the circuit we've got. Oh, hang on. Yeah, it is the same. I just wanted to go through. I'm also getting my mind into where we are and what we've got to do as well. So shifted them over to there, and we've got a current I2 dash there as well. Shifted them all to one side. Essentially, now, that transformer, in terms of analysis, don't even need to be there. If we've got values for some of these components, we can calculate, if we knew the value of the generator voltage and the two resistors, we're going to do an example in a minute, but we could calculate the current flowing, yeah, which is the same. I1 and I2 dash in that circuit are exactly the same. They must be. There's one series circuit round there. Yeah. So we could find out, and if we find out that current flowing there is 5 amps, we then move that formula around, and we can transfer it back to the other side and find out what the secondary current is. Yeah, you kind of see that, and that's better shown with an example, really. But once you know, analyze this side, you then have to transfer it back. In the case of the current, find out that's 5 amps. Know what the ratio is. You then rearrange that so I2 is equal to A times I2 dash. That transfers it back to the other side, and we know then what the current is actually flowing in the secondary. Yeah, and the same with the voltage. If we analyse and find out, once we know the current, we'd then be able to find the voltage across that Z2 dash there, and then divide that by A squared to transfer it back, divide it by A to transfer back to the other side. Yeah? Alright? There's absolutely no reason why you couldn't do the opposite thing and transfer everything to the secondary, although that would seem a bit weird to me. I think transfer it to the primary, you can then see a circuit with a generator connected to it, but it is possible to work the other way. I've never seen anybody do it, but it's possible. You have to transfer everything, including the generator, over to the secondary side, And then you could do your calculations and transfer back, and that would be exactly the same thing, except the other way round. All right? So that's the principle of it. And then I remember now why we had this like this, because I can then put component values on there and do an example. Did Steve do an example with some numbers?
Yeah.
To do an example on the basic one with some numbers?
Yeah.
I want 500 volts generator voltage,
Yeah.
Z1 10 ohms,
Yeah.
Z2 5 ohms by any chance, was it? Yeah. So you kind of saw the principle there, because you calculate Z2 dash is equal to A squared times Z2, 125 ohms. Yeah. The secondary transferred to the primary side, A times E2. Hang on, let's have a look here. Eventually, we end up with I1 is 3.7 amps. Yeah? Transferred back, that's 18.5 amps on the secondary. Is that what you got? Secondary voltage, 92.6 volts. Yep. Does that look right for a 5-times step-down transformer? Starting off with 500 volts, ending up with 92.6. Where's the other gone? Yeah, but in this model, where's it gone? In this model, where's it gone? New page. You have this is the generator and its terminals, and you got 500 volts, and then you got this impedance here, 10 ohms. Yep. And then you transferred to get Z2 dash there. Yep. And you got I2 dash there. Okay, and then there was your transformer that you had in the first place. So that's the model with the impedances transferred. Yep. And then when you've done your calculations, you've found, here's my generator again, there's my 10 ohms, putting it back with the transformer in the circuit, and what was that impedance? That was 5 ohms. Going by the results, we got a current there of 18.5 amps. Primary current was 3.7 amps. Yeah. You'd expect this one to be 5 times bigger. Is it quite 5 times bigger? 5 times 3.7. Ain't quite, is it? Is it? Okay. And we've got a secondary E2 of 92.6 volts. Yeah. This is 500. We got a 5-to-1 step transformer. You'd expect that to be 100 if that was ideal. So where in that model has the 7.4 volts gone? basics. Volt drop across there. Yeah? What you must remember with this analysis is the only two places you can put your meter and measure is there and there. You can't get on M terminals. That's ideal transformer. I'll explain that better when we do the real transformer model, right? But the only places you can measure are where that load's connected and where that generator's connected. There'll be other components between those terminals and here that are representing the losses, and you can't measure those voltages. But that's where that's gone. That would more likely be representing the resistance of the windings in the primary side when we come to do the real transformer model. Right? So we got a little bit of inefficiency already from doing that. Yeah? Alright? Everybody reasonably happy with that? Yeah? Or not? Then we came on to a circuit with some complex numbers, yeah?
We got to the end of that. Well, we wrote down the equations, but we'll never work out.
This last one, ideal transformer in a circuit has a turns ratio 1 to 50. Calculate the voltage E and the current I, and it, because it's got an inductor and a capacitor in it, it involved some complex arithmetic, yeah? Alright? So we'll go through that, should we? Yeah? So we're going to use transferring impedances. First of all, I is equal to N1 over N2, 1 over 50, which is 0.02. We're going to need that, aren't we? Generator voltage is 80 volts. Let's put that on there. All right, and we've been given the capacitive reactance because we got it in ohms. Okay. Yep. Next, what do you think we do next? Because we got a resistor here as a load, and we got a capacitance as well in series. Could do, but how might we do it slightly better than that, do you think? We could do that now, but I don't think that's the best way to do it. Move them over one at a time. 2. ZC dash. So we'll move the. Sorry, we'll do the resistor first. What do we need to consider now? Now we got capacitors involved. Need to consider the angle. do you think about what we're going to be doing here? All right, what's the angle associated with a resistor? 0. So this is going to be I squared times ZR. That's I squared times 40 kiloohms. Yeah. Angle 0 degrees. And actually, we need to deal with the kiloohms here. Pushing the buttons on that, you should get 16 ohms, angle 0 degrees. Yeah. So that's the resistor load moved over on the secondary side. Yeah. 3 ZC dash is I squared ZC. That's 0.02 squared times 30,000 angle. Angle for capacitor, minus 90 or plus 90? Minus J in it. Yeah? Plus as inductor. That is 12 ohms, angle minus 90 degrees. Yeah. Okay. All happy with that so far? Yeah. So what we've got now is this circuit. A 5 ohm inductor. So the angle associated with that is inductor 90 degrees. Yeah. We've got ZR dash, that is 16 angle 0 degrees. We've got ZC dash equals 12 angle minus 90 degrees. Tell me if I got any wrong, please. Yeah. And just as a reminder to myself and you, we're looking to find the voltages in the original circuit across the capacitor and the resistor. That's what the question's asking us to find. Yeah. So, if we find that voltage and that voltage, that's like VZR dash and VZC dash, we can then transfer them back using the ratio back to the other side. That's the idea of it. Alright? So what we've got to do now, how can we find those two voltages? We've got to find VZR dash and V ZC dash, then transfer back. Where are we going to start with finding those two voltages? Knowing that this one is whatever we give in the first place, 80 volts. How are we going to do it?
Now one's plus 90 angle and one's negative 90 angle, we can just get rid of the angles. I'll just be there,
Because I can't. Wouldn't that be lovely? If they were both 5 ohms, one at angle 90, the other angle 90.
It's not just
Yeah, but think about that. There's R. Yeah. Think about the triangle. We've got if that line and that line are equal, then they cancel each other out, and all we've got left is resistance. We ain't got that. We've got 12 and 5. Yeah. So that leads me to another question: is that circuit as it stands overall inductive or overall capacitive? Yeah, because the capacitive line is longer. Yep. All right. Bit of an aside, but that's what we need to expect it to be. Overall capacitive in nature. We can then look whether the current's leading or lagging, and does that fit as well. All right. So where are we going to start with actually finding out the value of those two voltages? What other value do we need to find that we haven't been specifically asked for? To find those, what do we need to know? Need to know the current. To find the current, what do we need to know? We've got 1 voltage and some impedances. Total impedance. Yep. Total impedances. ZL plus ZR dash plus ZC dash. Yep. Now, what do we need to do so we can add them together? Convert them to rectangular. So that is, we've got a 5 angle 90 degrees. How do we transfer that to? No. Doesn't need a calculator, do you?
Yeah, go.
0 plus 5J, 16 plus 0J, 0 minus 12J. Am I right?
On the first one, basically got more.
Well, we've got just an inductor. So there's 5 up, none across either way. So it must be just 5J. Because of the pure inductance, 90 degrees is straight up. So there's only an imaginary part, no real part. And then we've got a capacitance that is 12 downwards, only an imaginary part, minus 12J. So when there's only inductance or only capacitance, it's easy. Add them all together. What do we get? We got to add this column, 16, 5, minus 12, minus 7J, is it not? Yeah. And that is ohms, by the way. These are all ohms. All follow that so far? Yeah? Right, Matt? What are you doing for time? Now, we want to find voltage, which is going to involve us multiplying that current flowing by the impedance value. So what form would we rather have that current in? Multiplication, polar form. Convert to polar. So 16 minus 7J converted to polar. So it goes 17.5 ohms, angle minus 23. That's important, very important. We said it was overall capacitive, didn't we? So it needs to be negative, otherwise you know 23.6. All happy with that? So that's the total impedance. So now we can find these two voltages. Now find EZR dash. EZR dash is equal to I times ZR dash. Current. Oh no, we ain't found the current yet, have we? Didn't spot my deliberate mistake. I is equal to EG over ZT. It's 80, angle 0 degrees. Remember, if there's no angle given, it must be 0. It's over 17.5, angle minus 23.6. .57 amps, angle 23.6. That's minus 23. Remember, this is, when we divide, it's that angle, take away that angle, so it's 0 minus 23. The two minuses make a plus. Does that work with civil? Does that work with the word civil? Remembering that we said earlier The circuit is overall capacitive because of that negative angle. Overall capacitive, our current leads the voltage. It's got a positive angle. All looking good. Yep. Remember that? Richard, Matt, yeah? Yeah. So it's worthwhile just keeping an eye on that. Does it make sense? Because then if you like Lee just now done didn't put the negative sign in, you'd notice it. Right? Or you should notice it. So then we go on to find E ZR dash. So V ZR dash equaling I times E ZR. Sorry, ZR dash. That is 4.57 angle 23.6 times ZR is 16 angle 0 degrees. If you multiply 4.57 by 16, you get 73.1. That's volts, and the angle is exactly the same, 23.6 degrees. That must be true because resistors don't change the angle. Yep. Now here's the key. We don't want to know what EZR dash is. We want to know what EZR is. We want to know what that voltage is on the secondary side where that resistor is actually connected to. So now transfer back. To find E2R. E2R is equal to E2R dash divided by A. If you multiply to do it from one side to the other, you divide to go back the other way. That's 73.1 angle 23.6 divided by 0.02. Have I confused you, Richard?
I thought that was EZR, but it's E2R. Is that really down wrong?
Hang on. It is EZ actually, you're right. Yeah. EZR. That's the problem. As soon as you get Zs, Zs and 2s get muddled up when you write quick, don't they? That's like in electrical principles, we do a topic called Laplace transforms, where you put things in what's called S space, and they're impedances. And no matter how you try and come up with a problem that don't include any number 5s, one always turn up to get mixed up with your S's. Somewhere along the line in the manipulation, you'll always get a 5, even though you tried to come up with a problem that ain't got any 5s in it. Alright, so sorry about that. And the same with Zs and 2s. Okay? So what we're doing here is calculating, that's what the voltage is transferred to the primary, If we now divide by the transformer ratio, we'll find out what it is on the secondary side. We know a step up, so that's looking good. The answer to that, you should get 73.1 divided by 0.02, 3655 volts, angle 23.6 degrees. Doesn't change the angle. .1 divided by 0.02. What was the problem? What did he do?
He'd done it in the whole polar form at the top and then divided by 0.0, and I'd done that in the last question.
He can't do that.
He told me on the last question, and I could told him on his question.
Well, there might be calculators that you can now, but I don't think these ones do. All right. So does that look right? We got a 50-to-1 step-up transformer because the ratio is 1 to 50. You'd expect the voltages on the secondary side to be 50 times bigger than the primary side. So we're putting in 80 volts, right? Multiply that by 50. 4,000. If that was perfect, we'd have a secondary voltage of 4,000 volts. So we're in the right ballpark. Again, just have a little check. Does it make sense? All right? You're all happy with that? Yeah? So the voltage across the resistor, 3,655 volts. Yep. Now find EZC dash. I times EZC equals, I'll pause that now and I'll leave you to have. See you back here at 7-ish.
Yeah.
Alright, and I'm going to go and see if I can get them, have a coffee and get them results up. Alright, I'll do my best. Yeah.